So we're now in chapter 4, distance function and similarity search. Well, the reason why we're discussing this is one of the really important notions in data science is the notion of distance. Distance allows you to compare two different objects. Okay, so you have, let's say, one data row, one data sample that has certain features, and then you have another data row that has some other features. How do you know if they are similar to each other or different from each other? Ability to compare that is very important. First of all, we're going to see very soon that the notion of distance could be used for building a classifier. Okay, and then second, distance and similarity is an important ingredient for defining a unsupervised clustering algorithm. Okay, so clustering algorithms are basically for finding some latent groupings of the data points, and by when you define groupings of data points, you need to define the notion of distance. And distance is like sometimes so trivial that you don't even realize if distance is a problem or not. But if you think about it, the way that you define the distance is actually very important. A lot of time people just assume the simple Euclidean distance, right? The difference between individual components square, and then you take the summation of those square differences and then take a square root, right? That's the definition of Euclidean distance. But there are many scenarios where Euclidean distance does not really represent our semantic notion of similarity. So in those cases, you need to come up with a better distance metric. So that's one thing that's one of the objectives that we're going to learn from this class. The other objective, and this is very important and it's relevant to big data problems. If you have large data, algorithms that rely on distance computation, they usually rely on some sort of an exhaustive distance computation. So you have a set of, let's say, 3 data points. Okay, so you have 3 dots. Then you can construct a distance matrix, which is going to give you the distance between individual elements. So if I index these data points as 1, 2, and 3, then the distance between 1 and 2 is going to be the matrix element at the first row and the second column. And then the distance between the second data sample and the third data sample is going to be a matrix element at the second row and the third column, which is this one. Okay, so by doing this, and of course, and the diagonal terms are 0 because diagonal terms means distance from the first data sample to the first data sample itself, right? So the distance is obviously going to be 0. So diagonal components are going to be filled with 0. And then, distance metrics, we're going to see this condition as a distance function later, but distance functions are symmetric, right? So distance from Chicago to Iowa City has to be the same as the distance from Iowa City to Chicago, right? It doesn't make sense to have a different distance, right? So it's going to be a symmetric metric. So the lower triangle, doesn't become very important because it's going to be a duplication of the upper triangle. So, but at the end of the day, if we have 3 data samples, then we're going to have, a 3x3 distance matrix representing, the distances between different data points. Now, let's think about a situation where you have 100,000 data samples, or maybe, let's go big and, say 1 million, which is quite common in, large data analytics. So then you have 1 million data points, which means you need to create a 1 million by 1 million matrix. Okay. So 1 million by 1 million matrix representing the data, the distance between the data points. That sounds like a lot, right? So obviously, in order to compute this, then you're going to need quite a bit of computational time because you're going to need to evaluate all the components in this 1 million by 1 million matrix. So that's the first thing. The second thing is, if you think about it, the memory consumption is going to be another issue. How would you create a distance matrix that has a size of 1 million by 1 million? The size of the RAM are not that big. I mean, nowadays you can see, 512 megabytes, RAMs on the market, but still, I mean, if you have 1 million data points or, 100 million data points, I mean, there's no way for you to store all that information on a single RAM. So then, how would you handle all that? It's going to be a critical problem. So regarding that, as a first step, we're going to talk a little bit about classification problems. And in the classification problem, we're going to introduce an algorithm called the k-nearest neighbors that uses the distance information to make a classification of a given data point. You can actually use it as a regression, but since we've already seen a regression problem, let's try to discuss a classification problem. So this is something I have already explained about 2 weeks ago, right? In classification problem, we're concerned with a pair x and y, where x is our feature vector, and then y is the label. So exactly the features column in Apache Spark, and then the labels column in Spark. Those are the x and y. So for feature vector, there can be some arbitrary numbers, but y here in the classification problem can either be a discrete variable or the one-hot encoding. Okay, so the classification label y can be a numerical index, 0, 1, 2, 3, 4, such, or it can be a one-hot encoding. Okay, so that's the notational convention for classification problem. And then at the end of the day, what we'll be doing is essentially the same. We're going to find a function f that can predict the label variable y, the class variable y. Okay, this function f can have a form of linear equation. This you can decide to go with a more complicated model. Then in that case, the function f is going to be much more sophisticated. But at the end of the day, it's a mathematical function f, right? So x, the feature vector, goes in, and then the role of this function f is to produce either a discrete valued, the integers, or to produce a one-hot encoding. So we're going to talk about either of those two. Now, to have our conversation more, to have our discussion more kind of tangible and solid, we're going to talk about this toy example. This is a very famous example, by the way. It's called an iris dataset. So iris dataset is from 1936 paper of Fisher, and this guy basically introduced this dataset and then discussed about some problems of classifying different iris flowers. So in this data set, there are 3 different classes of iris. So iris setosa is one species of iris. Well, actually, I have in the next slide. So iris setosa is one species of iris. Iris virginica is another species, and then iris versicolor is another species of an iris flower. And if you look at them, they look quite similar, in fact, visually. And in the 1936 paper of Fisher, he introduced 4 variables as a feature descriptor. One is, the first 2 is the petal length and the petal width. And then the next 2 was the sepal length and the sepal width, okay? So by measuring the width and length of petals and sepals, Fisher found that there's a way to, taxonomically classify the 3 different species of iris. And in fact, this is a scatter plot showing the distribution of, sepal length and, in the space of sepal length and sepal width for 3 different species of iris. The red one is iris versicolor, the green one is virginica, and then third one is the cyan is iris setosa. So as you can see, there is some pattern, right? So for example, the red dots are quite easy to, see the distinction from the other 2. Again, here we have another scatter plot showing petal length versus sepal length, and then you can see that the red, green, blue are quite nicely separated already. Okay, And same thing, similar thing in different visualization, different parameters. You can see that they're quite well distinguished from each other. Okay, so using that linear regression formulation, classification is essentially, a problem of finding a line. Classification is obviously a problem of finding a line that separates, two data points, or two different classes. So obviously you can find a line, you can easily draw a line between the green class and the red class. And then green versus blue is not that simple, but I can do a fairly good job in separating them together. Again, it's not perfect because, as a result of that line, there are some flowers that are misclassified, but I guess it's not too bad, right? And in fact, we're in a four-dimensional space. And, since we're in a four-dimensional space, it is going to be much easier, although I cannot visualize that, it is going to be much easier to draw a line between two classes because, this one is, a projection of the four-dimensional space into a two-dimensional space. And during that projection, there's a chance that, the points that were actually originally separated quite well ended up, being projected to a plane where, the boundary gets, messed up a little bit. So, but nonetheless, that's one way of classifying different classes using feature vectors. Now, since that's something that we have already discussed, we are actually going to talk about something else. And the first thing is going to be the k-nearest neighbor algorithm. Okay. So this is kind of a unique algorithm in a sense that the classification task is not transformed into a regression task. So, I mentioned a couple slides ago that in typical classification problem, what you want to do is to convert a feature vector X using a mathematical function F and produce a, label vector Y. And that was a typical formulation of the classification algorithms. But in case of KNN, classification task is not transformed into a regression task. Rather, it relies on a sort of a heuristics, okay, that looks like this. So what this diagram shows is a situation where you have a data set, and then your data set is color coded using either yellow or red. So again, my favorite example, dog versus cat. So imagine the red dots are, feature vectors of dogs, and then the yellow ones are feature vectors of cats, okay? And then I have some high dimensional space where those feature vectors are represented as points, okay? Now, there's a gray one, which is a data point that I have never seen. So the red dots and yellow dots are the ones that I already know what they are. And then here's a new data point, new observation, represented by gray. And my job is to guess what this is, what this new point is. Is it a dog? Is it a cat? What is it? That's my job, okay? So as a matter of fact, search engines, for example, work in a very similar way. You know the class labels for each individual websites, okay? And then the user sends a query, and you need to somehow tell what that query is. Is this a website about, dogs? Is it a website about cats? Is it a website about, politics or, things like that? I mean, it is a very common task in, web applications. And what you've got to do is to rely on the existing data set, make a best estimation of what this new data point is. So in the sense of k nearest neighbor, what we're going to do is we're going to take a look at literally the k nearest neighbors. Okay, so what are the nearest neighbors from my existing data set to this new data point? So in the sense of one nearest neighbor, so when k equals to 1, if you look at it, this red circle over here is the closest data point in my database to this new query point, right? So one nearest neighbor algorithm which is an algorithm to find the nearest neighbor, the closest neighbor to the given point, the classification of this gray point is then going to be a dog, and therefore red dot, red color. Okay. Of course, when k equals to 1, then it can be quite sensitive to noise. So it is actually common to use something bigger than 1. So let's say now your k is 3. And if your k is 3, then these 3 dots are the closest to the gray dot over here. And in this case, what you do is, well, there can be many other strategies, but one naive but quite straightforward strategy is to take the popularity vote. Okay, so we have 3 neighbors, k neighbors. We have 1 vote casted for dog, and then we have 2 votes casted for cat, and therefore my decision, my classification on this new data point is going to be cat. Okay. So of course you can expand this to some k that is larger than 3, but typically we're talking about the range of k equal to 3 to 6 or 7, sometimes 12, but nothing terribly big. So usually around that range is kind of an empirical guess that I will make at the beginning. Of course you can tune the parameter based off of your experiments, but that's usually a good start as a KNN algorithm. So here's another example, another illustration of a KNN classifier in the context of classifying the iris versicolor, iris setosa, and iris virginica. So as you can see, the 3NN classifier has a decision boundary that looks a little bit funny like this. Okay, so the points that are in this region are going to be classified as iris virginica, and then the points over here are going to be classified as iris setosa. Okay, so that's basically how k nearest neighbor algorithms work. And what I plan to do was actually to have a breakout session where I give you 15 minutes to discuss how you could apply k nearest neighbor to a big data problem. So remember, there are 3 V's of big data. One is volume, the sheer size of the data is one important aspect, but there's also an aspect of variety and velocity. So if you think about it, you can judge if KNN is an appropriate algorithm for big data situations. Okay, so that was the original game plan, but I guess we're already, there's only 1 minute left for today's class. So we're actually going to come back to this next week on Tuesday, and then we're going to begin the class by having a breakout session. So try to be on time. And after that, we're going to start having some deeper conversation about what the distances are. And then eventually there's an algorithm called a Nystrom approximation, which allows you to compute distances in a very effective manner. So getting in there is going to be the objective for next week. So stay tuned for that. And thank you guys very much. And I'll see you guys on Tuesday.